All right, let's learn how to create some ray diagrams. We're going to be putting some lines on this drawing here that are going to represent two beams of light that originate from one location on our object. So I used the example in the classroom of a student sitting in the middle of the room, and I said, can everybody see the top of, whoever's head? So everybody in the classroom said yes. It didn't matter what side of the room they were on in reference to the student. That's because the light reflects off of this person in every direction. Remember, light, we said, travels in straight lines, so it's going to reflect off in all different directions. So what we are going to do for our ray diagrams is we're simply going to choose two of those beams of light, and we're going to show how those light rays move into the mirror and then reflect off of the mirror. After we have illustrated these two beams of light, then we will interpret their movement and determine what our image looks like in comparison to the original object. So the first step here says that we need to draw a line straight into the mirror. So if this is my student, we are going to say that here is my student. So this would be the top of the person's head, and we're showing how the light bounces off or reflects off from this person, and then this is going to be the light that we are going to have move into that mirror. All right, so first we're going to start off with one beam, and we're going to show how this first beam of light moves. So step number one says that we are going to take our object, and we're going to start at the tip of that arrow. Our object will be represented with arrows, and we're going to draw that object going straight into the mirror. So if you have a ruler, that is ideal. If you do not have a ruler handy, then just simply find something that is straight. But we are going to take some measurements from our drawing so that we can have some values and plug them into those equations that we learned in the last lesson. So having a ruler is really what you need. If you don't have a ruler handy, make your drawings for now and then come back later and do the math. If you'll notice, step number one says then. So we have two parts for this first beam of light. It's going to go straight into the mirror, and then because this is a mirror, it is going to bounce off. So we need to draw how the light bounces back to the left side of our drawing. It says that it's going to pass through the focus. Now, I need to clarify something for you here. Really, what we mean by this is that your ruler has to pass through the focus. You have to understand that you are illustrating the actual movement of the light. So we are going to draw straight lines to show where the light physically travels. If the light doesn't physically travel to that location, you need to ask yourself whether you need to draw the light over there, okay? That's kind of an issue that comes up quite a bit, and it gives the kids some real difficulty with some of these drawings because they're having a difficult time understanding what they are drawing. So when they get to this step, they're not really sure how to execute the through the focus part. For this first example, the light does physically pass through the focus. So we're simply going to take our straight edge or our ruler. Now, the focus is drawn in this case with a line. And so sometimes students will tell me that they are not sure what part of the line it needs to cross. That is a valid question. We are going to have a focal point. So where the focus is along that horizontal axis is what we are looking for. So we're going to take our straight edge and we're going to go from the mirror through the focus. So take your ruler so that it passes through the focus, and then you simply draw where the light is moving along that path. All right. Now, I have two parts to step number one. One beam of light goes into the mirror, and then bounces off. Notice that I put a vector, an arrow tip, on the reflected light. You need to make sure that you understand what light is actually received by the person. Remember the phrase, you see the light that hits your eye. So I put an arrow tip on the light that bounced off because that's the light that's going to hit your eye. So when it's time to interpret our drawing, when we're done with our illustration or with our ray diagram, you need to know which segments of the blue need to be interpreted. So the arrow or the line that comes out of the mirror is all we're going to pay attention to when it comes time to interpret our drawing. Step number 2, we are going to go through the focus, along the focus, put your ruler so that it goes through the focus so that you can understand the path that the light is traveling, all right? All different ways to say it. Some are clearer than others. In certain circumstances, some are going to be helpful and others not so much. So we are going to interpret through the focus as meaning put your ruler on the page so that your ruler passes through the focus. This is going to allow you to see the path that the light is traveling along. We are starting from the top of our arrow. We are going through the focus on our way to the mirror. Then, because this light is going to reflect, then this same beam of light is going to bounce off so that it goes straight out of the mirror. Once again, please feel free to utilize that horizontal axis on our drawing as a visual guide to help you recognize that we are indeed drawing it straight out of the mirror. Accuracy with your drawing is vital. If you do not draw your picture accurately, number 1, the picture itself will be counted as incorrect. Number 2, we're going to take some measurements from our drawings, and these measurements are going to be used to perform calculations. So if your drawing is off, your measurements are off, which means your calculations are off. All right? Okay, so step number 2 is complete. The second beam of light from the top of the arrow into the mirror and reflecting off. Step number 3 is actually giving us information about how we are to interpret what we just drew so that we can figure out what our image looks like. Once again, you have to understand what these lines represent, and remember that we see the light that hits our eye. So I put the arrow points, on the blue segment that bounced off of the mirror because that is the actual light that's going to reach my eyeball. I put the arrowhead on the last part of the second set of lines because that is the light that's going to actually strike my eyeball and send the information to the brain. Okay, so when it says for step number 3, the point of intersection represents the location of the image, sometimes students are a little unsure about where they're supposed to put their point of intersection because they look at this drawing and they see 2 points of intersection. This beam of light is what reaches your eye. This is all that your brain is aware of existing. This is the beam of light that reaches your eye. This is all the brain is aware that exists. So it's the intersection of these 2 lines that we're going to use as our point of intersection. So this right here is our point of intersection. Now, at this point, we have created an intersection, but we need to turn this into an image. Let me explain how we're going to create our image. You can see that the object originated from that horizontal axis, and then the line was drawn away from that horizontal axis to the tip of our arrow. So we're going to do the same thing with our image. We're going to start from this horizontal axis, and our line is going to be drawn away from that horizontal axis to the tip of our arrow, or in this case, our point of intersection. This point of intersection represents the top of my arrow. So this represents the top of my arrow. So this is what my image should look like. Okay, so the pink arrow represents the image. Now we have some words that we need to choose in the statements below, and then we're going to give ourselves some information. This is going to serve as your guide when you do your practice work. So you're basically writing yourself instructions or reminders of how to interpret the drawing. The image is larger or smaller than the original object. Well, here's how you're going to make that decision. If you recall, when we learned about vectors early in the semester, we said that the length of the line represents the magnitude. That is true once again. The length of the line on this arrow is going to represent the magnitude. So I am simply going to compare lines. The line for my object is this long. The line for my image is that long. Indeed, my image has a shorter line than the object, so the image is smaller than the original object. You need to then give yourself an explanation. I know this because. I would say because the line for my image is shorter than the line for my object. One of my students said because the point of intersection is farther away from the horizontal axis for my image than it is for the object. That works as well. Make sure that you write some sort of answer or description here. The next statement. The image is upright or inverted compared to the original object. My image is inverted in this case. Now, how are we supposed to know that? Well, I drew an arrow. The object is an arrow pointing up, and my image is an arrow pointing down. So, perhaps we can say it's because of the direction that the arrow is pointing. But here's the problem. My students don't always know what direction to point the arrow when they're trying to draw the image. So if that is you, if you do not feel like you are confident that you know what direction to point the arrow, there is another way to determine whether it should be inverted or upright. If the point of intersection is below the horizontal axis, then my image is inverted. If the intersection point is above the horizontal axis, then my image is upright. So in this case, I know this because the point of intersection was below the horizontal axis. The last statement says the image is real or virtual. This is where it's really important that you understand the lines that you put on the page, where they came from and what they represent. This is a real image. I know this because the lines physically met up to create my point of intersection. Now, when we do these drawings, you must use solid lines to represent the actual physical path of the light. So in this example, the solid lines met up on their own to create a point of intersection. So that's what makes this a real image. The light physically met up at a location. That's how you create your drawing. That's how we'd interpret what the image should look like from our ray diagram. For your assignment for the word problems that corresponded with the mirror notes, you were being asked to perform some calculations where you interpreted information given to you from a word problem. We used the formula 1 over f equals 1 over di plus 1 over do, and we plugged in some numbers to calculate whichever of these variables they were asking for. I'm going to ask you to do that again today using the drawing that you just created on your paper. We are going to calculate where our image should be located, because the paper that you received gave you the focus and the distance to the object. All you have to do is measure those with your rulers, and you know what those values are. The only unknown was where the image should be located. So we are going to rearrange this equation so that we solve for the distance to the image. So this is going to be 1 over f minus 1 over do. And then remember, everything is 1 over. So once we do that subtraction, we're going to then invert our answer to find out what our di equals. So for this question, you have to do the measurements. So grab your ruler, make sure you're using the centimeter side. We are going to measure how far away all of these things are from the mirror. So if we measure from the mirror to that focal point, we should get a distance of 1.8 centimeters, or something really close to that. Some of you might say 1.9, some of you might say 1.7. We should all get the same value, but I'm going to go with 1.8 centimeters. So from the mirror to the focus, this length right here is 1.8 centimeters. So we're going to take that value and we're going to make that 1 over. We're going to invert it. Minus. Now we need to measure the distance from the mirror to the object. And I noticed in class that there were several students that were a little unsure as to where exactly they needed to place their ruler in order to acquire this measurement. I want you to measure from the mirror to the object here along this horizontal axis. We don't want to measure from any other part of our mirror because it's curved. So the curvature is going to cause some variation in our distance. We want it to be measured along that horizontal axis. So once we perform that measurement, we should get a distance of 5 centimeters. Again, some of you may say 4.9, but I'm going to go with 5 because that's what I measured. And then before we put this in our calculator, we cannot forget that in our notes we were told that converging light rays are going to provide a positive focal length and diverging light rays are going to provide a negative focal length. So you need to pause before you go to your calculator and you need to determine, is this mirror going to give me a positive F or a negative F? In this case, we have a positive F because if you recall from the notes, for a mirror with this shape, the light rays that came in bent so that they ended up joining up together, and so this is converging. So converging light rays have a positive F for the focus, so that just means I'm just going to use 1.8. So in your calculators, do 1 over 1.8 minus 1 over 5.0, and then you're going to take that answer and you're going to invert it. And once you put all of that in your calculator, you should get an answer that rounds to 2.8 centimeters. So this tells me DI is equal to 2.8 centimeters. Now, if we look back at our notes, we learned that a positive value for DI means that we have a real image. So positive DI means we have a real image, and we do. Okay, that's what we already said from our ray diagram interpretation. Now you are also being asked to calculate the magnification. We are going to choose to use the negative DI over DO. If you wanted to, you could use the height ratio to get the magnification, but we're going to go with the DI/DO so that we can also get a positive or negative, so that we can interpret whether it's enlarged or reduced, as well as whether it's inverted or upright. So our formula for magnification is going to be negative DI over DO. So we're going to plug in the numbers that we already measured from earlier. We have a DI that we actually calculated, so we're going to do negative of our calculation. Now, in your calculator, you probably have more detailed information than 2.8. So please remember to use that answer function so that you're getting all of those decimals from the DI that we calculated in the last problem. Divided by the DO that we measured from the picture, and we said that that was 5. So when you put this in your calculator, you are going to get a value of negative 0.56. Remember that this is a magnification. Remember that our magnification is a ratio, so there's no units here. So what does this calculation tell me about my object? Well, remember the fact that it's a decimal, we said means that my image is smaller than the original object. So the fact that we have a decimal answer here tells me that the image is reduced in size compared to the original object. And so that's what it means on this first bullet here, where we said that it's smaller than the original. The other piece of information that we can interpret is whether this is an upright or inverted image. So if you recall from the notes, we said that if we calculate a negative value for our magnification, that means that our image is inverted. Looking at our notes, that's what it tells us. Looking at our picture, sure enough, we drew our arrow upside down. It is inverted. All right, so my answers over here are M should be a negative 0.56, no units. DI is a positive 2.8. Go ahead and leave your answers in centimeters for these ray diagrams. My focus for you is creating the illustration and understanding how to pull the data off of your own diagram in order to do the calculations. I'm not concerned with having you add that extra step of converting, so you can leave your answers in centimeters for this assignment. All right, we have one more example. This is also a mirror. So we are going to still show how our lines or our light goes into the mirror and bounces off. So we're using the same set of instructions that we did on the first example. So step number 1 says that we're going to go straight into the mirror. So once again, we are coming from the top of our object, which in this case is an arrow. Do your best to make sure that your ruler is straight into the mirror, then through the focus. So let me repeat myself. This means that your ruler goes through the focus so that you can see the path that the light is going to follow. You are going to use solid lines to draw how the light is actually going to bounce off of your mirror. So just trying to get myself lined up here. And again, we want to cross where the focus meets our horizontal axis. So this is the path that the light is actually going to reflect off. So this is the beam of light that's going to reach your eyeball. The second beam is going to go through the focus to the mirror. Again, take your ruler, put your ruler so that it goes through that focal point, but you're only going to draw the actual path that the light will follow with those solid lines. So I'm going to stop when I get to the mirror. My ruler goes all the way across, but the light does not. Because this is a mirror, it is going to bounce off. It is reflected. So from here, we are going to lay our ruler so that it's parallel to that horizontal axis. And we're going to show how the light then bounces straight out of the mirror. Okay, once again, you only see the light that hits your eye. So if I am standing so that the light bounces to me, I'm over here somewhere because in order for it to reflect, it has to come towards my face. So this is the beam of light that reaches my eye, and this is the beam of light that reaches my eye. So we have to find where these two beams intersect. Well, right now, they do not intersect. So does this mean that there is no image? Well, in this case, no. Only if our two vectors were perfectly parallel would they never intersect. These lines actually intersect. Remember, your brain does not know that this is a reflected beam of light. Your brain says, here is the light that comes to my eye. The light travels in a straight line, so it came from back here somewhere. Here is the other beam of light that reaches my eye, and my brain says light travels in a straight line. So your brain thinks that that light originated along this path. So that's the gist of what we're going to do. We're going to have to backtrack and figure out where is that intersection point. So let's do this accurately. We are going to take our ruler and we're going to extend our lines. Now, there is often some confusion as to which line needs to be extended. The light that I just traced is the line that's going to be extended. The light that reaches your eye is all that you can interpret. So take your ruler, put it back on the page, line it up once again with the focal point. Now remember, solid lines represent the actual path of light. The light does not actually penetrate through the mirror and go into the wall on whatever wall the mirror is hanging on. So we're not going to draw a solid line on the other side. But what we're going to do is extend it with a dotted line. Dotted lines represent virtual beams of light. These are the pathways that do not physically exist for the light, but our brain believes that that path is there. It is a virtual path because it is something that our brain is making up because it's trying to make sense of the information it has received. Now, after I extend the first beam of light, I still do not have a point of intersection. So that means I'm going to have to extend the second beam of light. Put your ruler back on the paper. Remember, this beam of light was bouncing straight out of the mirror. So we want our ruler to be parallel to that horizontal axis. This also must be a dotted line because this is a path that your brain is assuming. This is not the actual path that the light is traveling. Now we have a point of intersection, and that is this location right here. So once again, we are going to draw our line so that it originates from the horizontal axis. So we are going to draw, in this case, up to get to that point of intersection. That point represents the tip of our arrow. So this is what my image looks like. So now let's complete those statements about our diagram. The image is smaller than the original object. I know this because the length of the line for my image is shorter than the length of the line for the original object. Make sure you write in an explanation here. The next statement is inverted or upright. This image is upright. I know this because the point of intersection is above the horizontal axis. The image is real or virtual. This is a virtual image. I know this because I had to extend my light using dotted lines in order to create a point of intersection. The light did not physically meet up on its own. If so, my straight line arrows would have met up somewhere. Okay? That's how we identify real or virtual. If one line has to be extended with that dotted line so that we can create a point of intersection, then we're going to classify it as virtual. Either they both physically meet up or it's virtual. All right? Let's do our calculations. Once again, you need to take your ruler and you need to measure what you have created on your paper. So once we measure our focal length and our distance to the object, we can then perform our calculation using this formula where we are solving for the distance to the image, which is going to be 1 over f minus 1 over d, and then we're going to take those values and invert whatever that came out to be. So the distance to the image is equal to 1 over my focus, which on your paper should be a value of 2.5, minus 1 over the distance to the object. Again, we're measuring these from the mirror. So on your paper, that should be a value of about 1.9. Some of my classes said 2.0, some classes said 1.9. We should be relatively close. It was probably about 1.95, 9.5. We'll just go with 1.9. After we subtract these, we're going to have to invert that. But we're not ready for our calculators just yet. We have to remember that this must be interpreted as being converging or diverging light rays based on the shape of the mirror. And that's going to tell us whether our focal value should be positive or negative. So if you recall from the notes, this shape of the mirror, or if you recall from class, when I took the light and I made the light shine in and hit our mirror at different places, these beams of light bounced off so that they spread out in different directions. We called this diverging, and if you look in your notes, diverging light rays are going to have a negative F value. So we have to make this a negative 2.5 before we can do our subtraction. Then we're going to take that answer and invert it. After you do that calculation, you should get a DI value of negative 1 point, and it should round to 1.1 centimeters. Now, when we get a negative DI, that tells us from our notes that this is a virtual image. And if you look at your drawing, yes, indeed, you needed virtual lines in order to create that image. The second calculation is our magnification using negative DI over DO. So we are going to plug in a negative of our calculated DI, which I'm going to write as negative 1.1, but you're actually going to use the negative 1.0, whatever you got, the unrounded number, divided by the distance to our object. And that is going to give you a value of 0.57 once we round that off. Now, our magnification tells us two things. This is a decimal value, which means that our object should be smaller or reduced in size compared to the original object. If we look at our magnification value, this says that we're just over half the size of our original object. So if you look at your arrow that you drew compared to the original arrow provided for the object, it should be a little bit more than half, pretty close to half the arrow length. So double check to make sure that everything is accurate. We also can interpret whether this is inverted or upright. Remember, when we have a positive value for our magnification, that tells us that our object is upright. And that is indeed what we drew in the picture. So my DI was a negative 1.1 centimeters. My magnification was 0.57. Positive value for our magnification, no units because it is a ratio. These are the two examples that I had planned out for us. Now, I'm going to go ahead and move into the practice problems simply because there is a specific question that students needed some assistance with. So I'm going to go ahead and address that with you guys. When we get down to question number 3 on your practice assignment, there's some confusion as to how to execute steps 1 and 2 because of the location of the focus. So that's what I want to go over with you. Our first beam of light is going straight into the mirror. Then it is going to reflect so that it passes through the focus. Again, you are lining your straight edge so that it passes through the focus. You are using solid lines to draw the actual path that the light will travel. And then make sure you know which beam of light you need to interpret for your image. The second beam of light, it says through the focus on its way to the mirror. And here's where the confusion comes. You take your ruler and you line it up, and I'm going to show you what not to do first. A lot of students want to say, oh, well, it goes through the focus. Guys, is that light going to bounce off of the mirror? No, it's not even going towards the mirror. Are we going to draw a line going from the object away from the mirror if we're trying to show a reflection? No, that doesn't make any sense. Some students are tempted to take this line and draw it into the mirror, but then they feel like they need to do a dotted line to go through the focus. Guys, is our eye going to see this path of light? No. This is the light that goes into the mirror. This light does not reach my eye. My brain does not know that this beam of light exists. It is not going to try to fill in the missing pathway because it's not aware of this light's existence. So, yes, draw it along that path into the mirror, but this is all you're supposed to draw. From here, it's going to bounce straight out of the mirror. There is no point of intersection. All right, no big deal. We've seen this before. We're going to take our ruler, we're going to put it back on the paper, and we are going to extend the light that hits your eye. We see the light that hits our eye. So, bouncing straight out of the mirror is the light that hits our eye. So that is the light that we are going to extend with dotted lines, because this is not the real physical path of the light, but this is what our brain believes is making up. Our mind is being tricked to think that the light followed this path. So we fill that in with dotted lines because this is the virtual path of light. I still do not have a point of intersection, so I need to extend the other line. Again, only extending the light that hits your eye. So put your straight edge down and backtrack with dotted lines this path, because that is where your brain believes the light came from. Now you have a point of intersection. Now you can complete your image. And that's what your image looks like. And then you'll answer the corresponding questions